Hi, and welcome to College Algebra 2.1 Right Triangle Trigonometry. So, with this, we're going to really work on remembering some of these things we haven't quite touched on this year. So, the first thing we should talk about with right triangle trigonometry is, well, having a right triangle. So, here, when we have a right triangle, we obviously have a right angle. And the big thing to remember is always opposite from the right angle is the hypotenuse. Now, the hypotenuse is important, but we should also pick one angle. So in this case, I'm picking this angle. I'm going to call it A, where I'm going to put this little symbol theta. This is theta. It's a Greek letter, whereas this one is alpha. But let's talk about theta here for a second. From the perspective of theta, I have a side that's next to it, which I'm going to call the adjacent, and I have a side that is across from it, which I'm going to call the opposite side. From this, I have an adjacent, an opposite, and hypotenuse. I can use the SOHCAHTOA denomination to identify trigonometric ratios, where sine is the opposite side over the hypotenuse, cosine is the adjacent side over the hypotenuse, and tangent is the opposite side over the adjacent, hence so sine opposite over hypotenuse, cosine or cosine adjacent over hypotenuse, TOA tangent opposite over adjacent. Now, with those three trig ratios, we also have three more trig ratios that are flipped versions. So cosecant and sine go together. Cosecant is flipped sine. So instead of opposite over hypotenuse, it's hypotenuse over opposite. Secant is opposite cosine, so that's going to be hypotenuse over adjacent. And tangent and cotangent are inverses, so that's going to be adjacent over opposite. So in this case, from the perspective of theta, my opposite is y. So sine, being opposite hypotenuse, is going to be y over r, because r is identified as our as our hypotenuse. And cosecant would then be r over y, because it's just flipped versions of the fractions. Cosine would be x over r, and secant would be r over x. Tangent's going to be y over x, because it's opposite over adjacent. Cotangent would be adjacent over opposite, so x over y. All right. So SOHCAHTOA, sides are opposite of angles. So for example, what I mean by that is if I have big A as this angle, the side directly across from it, I'm going to call little a. Now, we often use C as the hypotenuse just to get in line with what we're going to talk about later, which is the Pythagorean theorem, which is a squared plus b squared equals c squared. C squared has to always be the hypotenuse. So you'll often see little c as the hypotenuse, therefore big C being the right angle. An important distinction, adjacent and opposite are relative to the angle being used. So from the perspective of A, little a is my opposite, and little b is my adjacent. But if I were to draw the exact same triangle, need more room, b, a, little a, c, little c. If I'm talking about the perspective of B, C is still my hypotenuse. That hasn't changed, but now the side next to my angle is A. So A becomes adjacent, and now B is my opposite. So the adjacent and the opposites can get flipped. So that's important to note. Let's see what that does. So let's say I was doing all 6 trig ratios from the perspective of S. From the perspective of S, 13 is absolutely my hypotenuse. 12, it's the side next to my angle. It's absolutely my adjacent. 5 is clearly across from my theta, so it has to be my opposite. So when I go to do, again, so TOA, sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. We get 5/13, 12/13, and 5/12. And then obviously the cosecant, secant, and cotangent just being flipped versions of those. But let's say I'm doing it from the perspective of R. Again, 13, still my hypotenuse. But now 5 is my adjacent instead, and 12 is my opposite. So my opposite and adjacent become flipped, which means instead of sine being 5/13 from S, the sine of R is 12/13. You'll notice that this 12/13 actually exists in the other set. Whereas this 5/13 also exists over here. Because of how the sides work and the angles, we find this little fun fact that sine of theta equals cosine of 90 degrees minus theta. All that really means is if you flip angles, your sine and cosine swap. So by that extension, the exact same thing happens with your cosecant and your secant. So I guess cosecant and secant swap. And then, funnily enough, cotangent and tangent swap. Because you'll see 5/12 becomes 12/5, 12/5, 5/12. Now, where did I get this 90 minus theta? Remember that, as it turns out, if I have 3 angles of a triangle, they add up to 180, and this angle right here is 90. So I know that theta plus alpha equals 90. Therefore, alpha equals 90 minus theta. And inversely, theta equals 90 minus alpha. Okay. The unit circle. So the unit circle is interesting. We have cosine of x is the first coordinate, and sine of x is the second coordinate. So cosine kind of goes for the x values. Sine kind of goes for the y values. We often call it, as all scholars take calc, quadrantial angles, negative angles. When I talk about negative angles, so if you look at it, we're going to look at it here in a second, get a quick peek here. So we always start by forming our angle along the positive x-axis, so along this value here. So I would always start my angle right there. Now let's say my angle, for the sake of argument, is right there. If I am going counterclockwise, I have a positive angle. If I am going clockwise, I have a negative angle. And if I look at it, you'll see that. So if I start 0 and I go up to here and I form a line right here, I'd have a positive 30 degrees. And if I kept going all the way to here, I have 330 degrees, because a full circle will be 360 degrees. And you'll even see these coordinates along here. Now the unit circle is derived. You'll notice that if I look at the coordinates along it, it's centered at 0, 0, and I have coordinates 1, 0, 0, 1, -1, 0, and 0, -1 along the axes. which means if I draw a distance from the center to one of these edges, it only goes a total distance of 1. So by definition, the unit circle has a radius of 1. And that's actually true for every single value. This is a distance of 1 from the center. Now, where do these values come from? Great question. Well, let's say I were to look at it. And for example, I am looking at this line right here that is 30 degrees along right here. Well, I can turn this into a perfectly right triangle. And given that coordinate right there is square root 3 over 2 and 1/2. Square root 3 over 2 and 1/2. That's this coordinate right here. Well, if I think about it, it all started at 0, 0. So this total distance would be just the change in x. So that total distance has to be the square root of 3 over 2. And this vertical distance is the change in y. Well, again, if I start at 0, 0, the y value here is also 0, so this total value would be 1/2. I just told you the radius is 1. Well, and the radius in this case is modeled by the hypotenuse of this new right triangle that I have. So if I were to do perspective from any one of these angles, I could always use Pythagorean theorem. So if I did the square root of 3 halves squared plus 1/2 squared, I would actually get 1, which is actually kind of cool. I would also be able to differentiate and find these sides if I didn't understand where they were at. So for example, again, say I have this angle right here. And again, I know that this radius is 1, and I know that this angle is 30 degrees. And I was trying to find this y component. Well, that y is my opposite, and 1 is my hypotenuse. So I could do sine of 30 equals opposite y over my hypotenuse of 1. Interestingly enough, y divided by 1 isn't changing the value at all. So as it turns out, sine of 30 equals whatever y value this is. So I could type sine of 30 into my calculator. If I had it, just a second, please. All right, thank you. So sine of 30, make sure I'm in degree mode, of course, and we get 0.5, which as we said is 1/2. So we find that y equals 1/2, which is exactly what the unit circle says. And also again shows that whatever sine value I have is intrinsically linked to the y value. Now what does this all scholars take calc thing mean? Well, all three things are positive in this coordinate. Well, what I mean by that, the x values are positive and the y values are positive. So the x values are cosine and the y values are sine. Tangent's a little bit trickier. So let's talk about tangent. If sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, tangent is opposite over adjacent. What actually can kind of happen is, let's say, for the sake, I was to do sine divided by cosine. That would give me opposite over hypotenuse divided by adjacent divided by hypotenuse. Well, if I'm dividing two fractions, I can keep the first one the same. I can then flip the second one, so hypotenuse over adjacent, and I'm multiplying. Well, you'll see that hypotenuses cancel. So we get that that is opposite over adjacent, which is exactly what tangent is. So therefore, tangent is actually sine divided by cosine. Or in the context of the unit circle, tangent is y divided by x. So when I look at these, I'm looking at the y values and the x values. If I'm going to take a positive value divided by a positive value, I'm going to get a positive value. So tangent will be positive for all of these things. So that's what the all means. That's about quadrant 1. So again, if I'm in quadrant 1, all 3 trig ratios are positive there. This would be scholars. S is for sine. Sine is positive over here. So if I look at it, my x values, which represent cosines, are negative. And I would do a y divided by my x for my tangent. Positive divided by a negative would give me a negative value. So sine is the only thing positive there. Take is quadrant 3. As we can see, my x's and y's are both negative down here. But tangent is y divided by x. So it's a negative divided by a negative, which would be a positive value. And then calc. You'll see that if I look at it, all the x values are positive, so the cosines are positive there. Okay. Quadrants are reflections of each angle within also ours take calc. You'll also again notice that the numbers are very similar. Here I have positive 1/2, negative 1/2 for those x values, negative 1/2, positive 1/2 for, negative 1/2, negative 1/2, positive 1/2, positive 1/2 for the y values of reflection of where it is. You'll also notice again the numbers are pretty similarly chosen. We have a 30 degrees, we have 6 degrees, and 45 degrees. If I were to extend this line right here and look at that 30 degrees right here, this angle up here would have to be 60 degrees. If I did the exact same thing right here, well, this angle right here would be 60. This one up top would be 30. So it's just a flipped version of that exact same triangle. As opposed to here, it's the 45 degrees right here, so it'd be 45 up there, which means it's an isosceles right triangle. Functionally speaking, if you feel really comfortable with your 30, 60, 90 triangle rules and your 45, 45, 90 triangle rules, that's all the unit circle is doing. Anyway, thank you for taking the time to listen to that introduction, and I hope you have a wonderful day.